Let's look at a specific class of DACs called string DACs. Okay, and when you see the schematic, you'll know why it's called string DACs. So here's a schematic of a string DAC, which is a voltage input or a voltage output DAC. Okay, and as you can see, at the input there is a string of resistors here, and that's the reason why this is called a string DAC. Okay, what is this string of resistors doing? It is dividing this voltage reference into different values, right? So you have 0 here, and then you will have, let's say if you had 8 resistors here, so if you have 0 here, you will have Vref over 8, 2 Vref over 8, 3 Vref over 8, and so on. So you have different values of voltages coming at these different points. And then what these switches do is they select one of these outputs or one of these inputs or one of these voltages that are generated by this string of resistors to go as the analog output. Okay. Uh, so a 3-bit digital input is given. That is the digital number that you want to convert into an analog output. And what you do is you send it through a 3 to 8 decoder. Basically, what it does is it takes these three numbers and converts it into a 1 to n code. Remember, right at the starting, we looked at different kinds of digital codes, and it just converts it into a 1 to n code, which means that if the number is 1, uh, out of the 8 bits here, the first bit is high, and therefore this switch would close, and this voltage would appear at the analog output. If the digital input is 0, then the 0th bit is high, and therefore this voltage goes into the analog output, and so on. So that's how a string DAC works. Fairly straightforward. Let me just summarize. The Vref is divided into different values. So if you want to divide uh, uh, a range into 8 values, let's say you want to do a 3-bit conversion. So you take uh, a string of 8 resistors, give the V reference as the input, and then you uh, get voltages which are multiples of V over 8 around the string, right? And then you get one of these voltages to appear at the analog output using these switches. Okay, you could have string DACs which are current output string DACs. Okay, uh, ooh, I'm sorry about this. This should have been current output here. Okay, so again, you have a voltage input, but in this case, what happens is depending on which switch is on, you can have different currents flowing through I out. Okay, so if let's say two switches are on or two switches are closed, how much current is going to flow through here? To I out. You will have Vref over R here, and you will have Vref over R here, and therefore the current will be 2 Vref over R. If three switches are turned on, you will have 3 Vref over R, and so on, right? So Vref over R becomes the constant by which you're multiplying your digital input. Now, as you can imagine, the decoder here has to work a little differently than before, because if the decoder converts the 3-bit digital input to a 1 to n decoder, then the current in all outputs is going to be the same, because it doesn't matter whether this switch is on or this switch is on. The current when one switch is on is always going to be Vref over R. But if we are able to convert this 3-bit digital input into a thermometer code, remember what a thermometer code means? If the digital code is 2, then then the bits 2, 1, and 0 all are 1. If the digital input is 3, then the thermometer code would mean that bit 3, bit 2, bit 1, and bit 0 all are 1. Okay, you can go back and look up what a thermometer code means. So what that means is, depending on the digital input, there are different numbers of switches which are on, and that would give us different amounts of current proportional to the digital input. Now, one of the problems with this kind of a current output string DAC is that you are switching currents, right? So you have, let's say, no current at a particular moment, and then suddenly at the next instant, you want to have Vref over R. What that means is that it would take some time for the current to switch. Currents cannot switch immediately, just like voltages cannot. So one way of okay, and because of that, what's going to happen is the DAC is going to become slow because you'll have to wait for the current to reach its final value. Okay, so how can we make this faster? So one way of making it faster is by using this kind of a circuit where you have complementary outputs. So you have an output and an output bar. Okay, and what you do is, so these are current sources which could be formed by using resistors, right? And Vref, but I just drew it as current sources to just give you a different idea. And what we can do is, instead of the switching between the output and, so between a particular value of current and no current, what it does is it switches to uh, an output or a complementary output, right? So when the switch is off, the current doesn't go into the output, but it just goes into output bar. So which means that this current never is going to become zero. Okay, so this current source, the current through this path is always going to be the same. It's either going to flow into the output or it's going to flow into the output bar. And what this does is it just increases the speed of your DAC. And that's why you would see when you actually look at DACs that many DACs have complementary outputs, output and output bar, especially DACs which have current outputs.